here right now. But that's enough about me. So generally, when you're talking about access networks, you will at least want these three features. So you want to isolate the clients so they don't have any unwanted interactions or eavesdrop on each other. And you want non-repudiation so that you can, when somebody acts up, then you can blame them. And if the police come, you know that it's them. And they'll then get prosecuted and they won't be the wrong person. And hopefully you'll also be able to auto-configure the end-user host, so we don't have to tell everybody here a static address configuration. It might be a little inconvenient. And there's some essential IPv6. I really, really, really hope you don't have any problems with this. But it's just basic terms. We'll skip that. And then we'll go to a problem with NDP. So, well, everybody knows that if you have big subnets, they're a problem. So that's nothing new. But with IPv6, we're having /64s. They are really a lot bigger than anything in IPv4 ever. So that will never fit in any router's memory or cache or whatever, depending on the router. So you will have some problems. And practically with a 64, you can always exhaust all the resources of the router, even with one interface with 64 mask. And basically, the NDP processing router, well, if it's not a software router, it will be in the control plane CPU, and it has to be rate limited. And that's not a problem per se. With IPv4, we already have a global rate limit for the NDP, and it's not causing that much trouble. But what actually happens in the CPU is more interesting, because to avoid flood, they will have some kind of state for every destination address. And, well, with a 64 subnet, you have quite many destination addresses, so you cannot have state for every destination, whereas for a normal IPv4 subnet, you can. So with IPv6, you will eventually end up with a situation that the control plane resolver has state for this many next hops that it's resolving now right now, and then it's full. And then it's getting these, if you're getting more packets that have a next hop that does not have a resolve ND entry, then the router will act up. And it depends on the router what exactly happens, but generally the resolver will somehow stop resolving. So with IPv4, you have to fail the global polisher that protects the CPU. But with IPv6, you can actually have much less packets, because if you just have sufficiently many different destinations, it will then, the control plane itself will go. So this is an illustration of this attack. So it kind of looks like a scan. And probably to have any effect, it is not just any scan, it has to be longer than that. But it's just normal traffic, any kind of traffic that has addresses that don't exist, so the router cannot resolve that. And basically, well, this slide has pretty much what I already said. So basically also with neighbor discovery or ARP resolving, the router will always cache the first packet in its memory also. So it will have to keep it in memory, and then it will send it when it has resolved the next hop. But it's impossible to do that in IPv6, because you will have so many possible next hops with a 64 subnet. And the important point in here also is that you need to know your hardware and be aware what happens with your particular router, because the failure modes differ. And then there's this other problem that actually I have done this once also, but nothing happened. Nobody was attacking at the time. But basically, if you have a 64 given to you by your ISP, then it might be that you have want to put some kind of mailbox in there, and then you might configure proxy ND for the whole 64, or there might be an attacker doing that on purpose instead of a naive person. So whatever, if there are so many hosts in the subnet that they will not fit in the neighbor table of the router. It will then fill up. And again, with IPv6, if you have a per 64 subnet, there is never going to be any router that can have that many next hops ever. So then you will have the router table full, and probably if you have 1,000 or 10,000 useless hosts and maybe 100 real hosts, will mean that you will eventually have the real hosts evicted and the bogus ones in the table.
Actually, I think a couple of European internet exchange points had a sort of this kind of an attack, inadvertently due to software.
Yeah, exactly, and it kind of depends on the router. So different routers have different failure modes. But to work around this, there are quite many different things you can do. Nothing is perfect, but there are some mitigations. So there's a very obvious solution is just to use a longer prefix. So if you have less next hops, then less problems. And usually you will have in your addressing plan, you'll allocate a 64, but then configure a longer mask, and then you can shorten it if you need more addresses. And there's practically the only downside is that stateless autoconfig will not work. But stateless autoconfig, well, in some cases you want it, but it's often a reasonable compromise to live without it. But for example, in here, you probably will want it on the wireless LAN too. It's most easiest way to get these endhosts configured and most likely work. And there's also, of course, if you have stable firewall that does not allow any new sessions inside the inbound direction, or if it has an access list that only allows certain addresses inbound, then you cannot. The traffic will never come to the interface and never trigger neighbor discovery. So this will also hopefully help the tiny little CPEs that are routed, because they will maybe have a stateful firewall configured, because those little boxes will also not be very resilient against attacks. But of course, it will not help if there are insiders who want to attack. And also, if you have DHCP v6 and DHCP v6 snooping, you can then, well, the DHCP server will probably not give one guy more addresses than he needs, so it will prevent the other attack from working. And also, routers could be a lot smarter. This is probably the problem now, that routers are they're really stupid. So if you can't do rate limiting by destination address, then you still can't do it per interface and contain the problem. So for example, if you have an entry limit per interface, then the problem will mostly be contained for one interface. And if you have a reservation for every interface, you can also make sure that, for example, your core interface always has some neighbor table slots free, whatever happens. And if you have a limit for ND entries per one MAC address, then if there is a host that is doing proxy ND, it will not be able to have too many addresses. And if you have port security, then even a malicious attacker can't have more ND entries than you want. And also, there should be priority to pre-existing ND entries and statically configured ND entries. Well, you would hope things would be like that, but some existing routers have serious problems with that, and they evict existing neighbor entries in situations that cause problems. And of course, also, you probably want to have next hops and running vertical neighbors with a high priority. Losing ND entries for those would be quite inconvenient. And then there's, of course, rogue arrays, which are still a problem. Well, you'd hope that we could have solved it already, but it seems not. So, practically, arrays are the only way to auto-configure a default gateway for IPv6 hosts. And they have no authentication, so a single array will immediately point all the hosts toward a router. So it's a much more annoying problem than route DHCP, because a single packet is enough, and then all the hosts are fucked up and you can't fix them very easily, except, well, you can send another array which has a 0 lifetime, so it will then invalidate it, but still it's a much more annoying thing than rogue DHCP because it will, all endhosts will be gone at once. DHCP, it will take quite a while for every endhost to get the configuration. And also there are these few notorious cases that thankfully they have brought rogue arrays in the spotlight. So Windows boxes with ICS and some Apple AirPods and other consumer routers will get a 64 prefix and then send arrays with that prefix and cause all kinds of grief. So it's hopeful that we will get switches with array guard on the market and deployed, but it's a little problematic because it's a pretty small feature, and who wants to replace all the switches for that? It's going to be pretty expensive. And for example, if we think about a venue like this, when there's a small, tiny, cheap wireless access point that, well, you're not going to be able to buy one now today that does array guard. And if we actually want to deploy IPv6 everywhere, as we hopefully really want to, it's annoying that we can't fix rogue arrays in a simple coffee shop wireless LAN. It kind of feels like we have failed if we really want to have IPv6 to the masses. And of course, thankfully, private VLANs and those other pre-existing layer 2 containment techniques still work. So you might be able to do without array guard if your LAN isn't a flat, big, one single broadcast domain. Then there's something that actually has a little to do with array guard. So in IPv6, the packet header has a field called next header. And in IPv4, this was called a protocol, now it's a next header. So IPv6 has header chaining, so you can theoretically put as many extension headers after the packet as you want. In IPv4, you had options. It's a little analogous to this situation, but you can use these to evade ACLs. So if you stack extension headers after the IPv6 header, so that it's a really long chain, and then put your TCP or UDP or actual header after that, you will then be able to bypass some hardware ACLs because the routers only look at the beginning of the packet. And practically all the routers have some kind of limit. They cannot process a full MTU size packet. So they can't see the headers, they can only forward the rest and look at some of the first bytes. So there will probably be some interesting discoveries because routers will see the packet in one way and end hosts, depending on what kind of end host they are, will interpret it differently. And there will be interesting interactions and things you can do. For example, array guard might be implemented in a naive way in a switch. You might be able to make an array packet that will not be filtered, but will practically still, an end host will interpret it as an array. And same goes for TCP and other. So it's a problematic thing, but maybe new hardware will fix it. And then there's a little problem because the typical way that people want to deploy IPv6 is to have a layer 3 interface per customer. So it works pretty well if your hardware supports it, and it probably does. The only glitch is that if you have IPv4 addresses, you will not have a spare /30 network to assign to every customer. You probably want a shared subnet, especially if you have residential access. So you can have a little problem with this, that your IPv6 is layer 3 interface per customer, but you still want shared layer 2 or IPv4. Well, that problem will eventually go away, but it's still relevant. And on the other hand, if you have a network, an access network built for shared layer 2, it's also going to be quite a lot of work to bring layer 3 interfaces for every customer. And it's also a lot more work if you think a DSL access network, every port doesn't really need much configuration. But if you bring VLAN per customer, it's it's not going to be so easy anymore, and your switches might not support that many VLANs. But you can maybe use unnumbered sub-interfaces for IPv4. So that's a feature in the routers that will practically more or less make an unnumbered IPv4 interface that will make the different layer 3 interfaces look like they are in the same layer 2 network. And with protocol VLANs, you might also be able to put the clients so that the IPv4 and other traffic is in one VLAN, and then the IPv6 traffic is in a per customer VLAN. But the nice side is that you don't need any fancy things in the access switch if you have VLAN per customer. So no need for RA guard or anything else. Everything is in the router. But practically, the way the world now works, at least for mass access, is shared layer 2 and all kinds of interesting tricks in the access devices. And the problem here is that the access devices don't really support IPv6 really well. So, of course, you have DHCP snooping and IP source guard, but not that many vendors have it for IPv6. And it's a new feature, and it will take time that it's perfected for production use. So you will also have to forklift all your access gear to support this. So it's not really a very nice thing to do if you want to bring IPv6 to the masses and need to replace all your equipment. And even if the hardware can do these things, I have a feeling the vendors are not going to want to give it to us for free. And also, if you want to give routed subnets to your customers, even residential customers with a layer 2 access network, you will then need prefix delegation, and that's also a feature that's not really visible. With PPP access, you can get it, but that's not shared layer through. And well, at least I personally hope I will be able to get routed IPv6 at home, because it really sucks to have only one subnet. And also there's this annoying fact that rogue arrays are pushing some networks to upgrade now because they are a problem, but they might in a few years' time notice that the upgrade has not been really useful because maybe the switch only supports RA guard, but they will want the IPv6 snooping and other features. And it's kind of problematic. People are pushed to upgrade, but there's not very much available in the market right now. So the layer 2 access switches are kind of disappointing. So I hope you have questions or maybe comments on how you are solving these problems. I'd be interested to hear it. So anybody is actually deploying IPv6, or are you talking? Yeah. Yeah. So have you run into any problems? Yeah.
How many of you here, well, I want to ask a question first, then you can ask. So how many here have actually had to disable like rogue RAs or something, even though you haven't deployed IPv6 in any way? I guess we don't have, other than you, we don't have people from student housing organizations, because they usually have this problem even if they don't have any IPv6 in their network.
Yeah, currently now I get 64 arrays on my home connection from some Apple airport, and they can not really do much about it without replacing their switches.
Dave?
Just wanted to talk quickly about some problem that I have, which is that as we've got broadband deployments that are moving from the traditional PPP base to IPOE. Trying to do IPv6 OE in these sort of circumstances is hard, because the way that it's traditionally done is you put people on what appears to be a big flat L2 segment, but it's really something that's partitioned by the DSLAM, or the access equipment, filtering MAC traffic between subscribers and forcing them to a central point. And with IPv4, if you allow subscribers to talk to each other directly, which you wouldn't in many circumstances, but if you did, you do that with something such as proxy R. There's no such concept as proxy ND. Even though it's been talked about a lot, it doesn't yet exist.
Actually, it was mentioned on the
but
slides, but there's a problem.
Yes, it's a problem. There's no concept. And this is the problem we're facing. Being able to allow people to, we allow them to selectively discover each other through ND, and how do we mediate that? And from an access perspective.
Actually, there's another way to formulate that problem, because in the past we used to have NMBA media and broadcast media, and Ethernet was broadcast media. These days we don't really have frame relay or ATM or anything that used to be examples of NMBA. But the Ethernet we want to deploy for customers actually is NMBA after all. So maybe that is another way of looking at the problem. And then if we just look at how NMBA routing is sold for IPv6 and IPv4, and then we actually think about how to deploy it in our network, which requires, of course, vendor support, then that could be one answer to the problem.
Yeah, I think we'd want the benefits from MBMA and nothing else, to be fair.
I do not contest that.
Yes.
Yeah, but there's actually one problem even there. If you want non-repudiation, you'll have to do source address filtering for every customer, and it requires support from the access network at the port level, and practically nothing supports that now. So if you want to trace the troublemakers with IPv6, you're pretty much out of luck.
A colleague that has actually deployed an NMBA Ethernet network as a partial mesh VPLS.
That's one solution. Okay.
So to your previous question, we had one case when we had to deal with rogue RR. It was a Vectorama one-party event at Oulu, and there was this one computer at the LAN party who actually was Windows machine protected.
Actually, not only one, because on some versions of Windows Vista was the problem that even you don't have network sharing. If you have configured IPv6, it sent address, and it was.
Yeah, but I think we solved most of that problem then by just looking at the computers and walking behind the backs.
And actually, this spring, GEA, which is an organization for European National Research and Education Networks, hosted an IPv6 workshop in Espoo in Finland, where some of these issues were also talked about. And naturally, there were people from different universities all across Europe, and also student housing and other environments where they have huge subnets by necessity, that have, of course, all bumped into the problem, even though some of them didn't even support IPv6. And there were, I think there were more than one implementation from, I think, Poland and Czech Republic of software that sort of worked like RA guard without the cooperation of the switch. So one solution, for example, was that they sniffed the traffic, and immediately when they noticed a rogue RA, they faked the same RA with lifetime 0.
Yes, PAN Oulu, as far as I know, does the same.
Right.
Oulu. I think the whole network is one L2 network as in IPv4 sense, but the whole network is not IPv6 ready. I think there are parts that don't offer IPv6 support, but the whole network has some kind of RA card.
Yeah.
And
as Dave was talking to me yesterday, there's a problem with Macs when they see this RA with 0 lifetime, whereby because of a combination of two bugs, it treats it as an infinite lifetime.
Yes. This is now fixed in line. But,
there is, I think, an implementation called RA Fix that does that, shooting down the
Yeah.
rogue arrays, but it's a problem because these solutions are really whack-a-mole, so you
Exactly.
reactively run behind these problem makers and try to do something. Yeah.
Your address is because your email address.
Yeah. It's not missing anything. I tried it.
Yeah.
a few days ago.
Please send questions.
Yes, please.
Well, I looked it up and can't reach it.
Then I screwed up something, but it should work. So I'll fix it.
Okay, thank you for the presentation. And so now we take a 10-minute break, which means that we'll continue at 25 past for local.